Hello, from the Aunt Hall Studios. This is Dr. Royer with a lesson on functions from section 7.1. A function has three parts, and so we often draw Venn diagram type pictures to help show what's going on. There is a set called the domain. There's a set called the codomain, and if you were going to call that the range, we'll get to that after a bit. And then there's a rule that goes from set A, the domain, to set B, the codomain. And the key thing about the rule is that every member of the domain has to go to exactly one value in the codomain. So inside here there are various elements, and each of these guys needs to go to exactly one over here. The way you really understand that is to look at a series of examples, some of them a bit tricky. So here we go. Here's a similar sort of picture. I propose that a function go from set A to set B by the picture below. So we could do without the picture if we wanted a functional definition. It's a little clumsier though. F of 1 equals 2, f of 2 equals 4, f of 3 equals 10, f of 4 equals 10, and f of 5 equals 2. This picture and this list of definitions are exactly the same piece of information. Question, is it a function? Well, we have the two sets. We have a rule going from the domain to the codomain, and the distinguishing feature again is there exactly one output for every input. Answer, yes. Notice that it doesn't matter that f of 1 equals 2 and also f of 5 equals 2. Nobody said that two different inputs could not go to the same output, just that one input could not go to two different outputs, and it doesn't. Second example, let's propose a function from the set the integers cross the positive integers to the integers by this div operation that we looked at. So remember that, say, 7 div 4. What is this? Well, I'm supposed to think about 7 divided by 4. It goes once with a remainder of 3, and the div operation picks off the quotient, so this is 1. And so when we take an integer and we divide it in this way by a positive integer and just take the quotient, the question is, do we always get a unique integer? And the answer is yes. Division by 0 is not allowed, but it's not part of the definition of the function because the d number has to come from the positive integers. Third example, a relationship that goes from the rational numbers, that's what this means, to the integers, defined by h of m over n equals n. So things in the set of rational numbers can be written as fractions, and this is proposing that I just grab the denominator. Of course, that's not going to be 0. It wouldn't matter if it were anyway, I guess, because the 0 is in the set of integers. So the denominator, if I have it written as a quotient of integers, is certainly an integer, so no problem there. Let's try and show some examples then. H of 3/4 equals 4. H of 6/8 equals 8. But wait a minute. 3/4 and 6/8 are the same number. So I've just computed h of the same number and gotten two different numbers. This is a situation where 3/4 can produce 4, or it can produce 8, depending on which representation of the fraction that I pick. This can't be. This is not a function. It may look like it at first, but it is not. How about a function, proposed function called p, that goes from the positive integers to the set 0, 1, defined by p of an integer is 1 if the integer is prime, p of the integer is 0 if the integer is composite. P stands for prime, actually, so this is like a prime checker or a prime indicator. P of all the primes is supposed to be 1, P of all the non-primes is supposed to be 0. So P of 7 equals 1 because 7 is prime, but P of 9 equals 0 because 9 is not prime. Does this always work? Well, I'd have to conceptually check all of the positive integers. So here are a couple of them. Let's try one more. P of 1 is, 1 is neither prime nor composite by definition. And so this definition is not a function. There is a member of the domain. 1 is in the set of positive integers, but P of 1 doesn't produce any outputs at all. Before, the problem was one input gave two outputs. Now the problem is one input doesn't give any outputs at all, and the definition of a function is each input has to give exactly one output. Well, you're saying maybe that, well, it almost works, right? And so if I were to define Q from the set 2, 3, 4, and so on, all the rest of the positive integers to 0, 1, in the same way. So I won't write it, but that Q of n is 1 if the integer is prime, Q of n is 0 if the integer is composite. And Q is a function. So how can that be? Don't P and Q have the same rule? Yes, they do. They're checking whether the input is prime or not. But they're different functions because they have different domains. In fact, P is not even a function at all. They're different relationships. Q is a function. It can be a function because its input set is different than for P. Let's look at another. F from the real numbers to the integers defined by f of x equals, and you read this, floor of x. So the floor of a real number is an integer, and it's the integer for which x is at least as big as n, that integer, but less than the next integer. So f of 7.6. I want an integer which satisfies this relationship for x equals 7.6. Answer, 7, because 7 is less than or equal to 7.6, which is less than 8. And how about f of negative pi, about negative 3.14. So whatever we do, the reason has to be that negative pi is less than and greater than or equal to, like this. I have to put something here and then one more here so that the inequalities are true. And the right thing to do is put negative 4 here and negative 3, which is 1 greater, here. So negative pi, negative 3.14 satisfies both of these inequalities. And so answer, or output, is negative 4. I've just checked a couple, but you can keep doing this and you never run into problems with the definition. There always is a unique integer that works. Yes, this is a function. It's called the floor function, and for discrete math it's pretty important because for calculus type problems often the inputs come from the real numbers. In discrete math we were doing proof by induction and so on that was geared toward the integers, and so the floor function sometimes lets us take a problem from the real numbers and kind of move it over to the integers where we can talk about it with the techniques of this class. Here's a really scary one with weird notation going on. So let's let P of u denote the power set. Remember, that's the set of all possible subsets of whatever given universal we're talking about. So I propose a function that goes from the power set of 1, 2, 3 cross the power set of 1, 2, 3 to the power set of 1, 2, 3, if you're still with me. What I want to do is take one set that I'm given, another set that I've given, and take the union. So let's see. F of, and then a subset of 1, 2, 3 could be something like 1, 2. And a subset, another subset of 1, 2, 3 could be like 2. And so this definition, if it's a function at all, is proposing that I compute, all right, 1, 2, union 2, and when I do that, 2 is already in the first set, so this is again just 1, 2, and the question is this answer going to be unique? Could anybody get a different answer? No. And second of all, does it end up in the right place? Is 1, 2 really in the power set of 1, 2, 3? Well, yes it is. This is the set of all subsets of 1, 2, 3. This is one of them. So this works. And notice that this time the inputs to the function are not numbers at all. They're sets, things, other types of things that we've worked with in this class. Last example. A proposed function from z plus, the positive integers, cross z plus, again the positive integers, by p of n comma r equals the number of permutations of n items chosen r at a time. And so proposing things like p of 3 comma 1, number of permutations of 3 items chosen one at a time. This is 3. But how about p of 1, 3? That's allowed, right? 1 comes from z plus, 3 comes from z plus, and all of a sudden this doesn't seem so well defined anymore. 1 item, I'm going to choose 3 of them unless I agree ahead of time that repetitions are allowed, and we didn't when we were talking about this definition. Then this will be undefined. So at least with our standard definition of this symbol from before, that it meant permutations without repetition, this is not a function. I could come in here and adjust the second thing, so I could say that the set in the second slot has to be the set of integers that are less than or equal to the set in the first slot, so I avoid this second bigger than the first. And I could turn this into a function then in the same way that we did number 4 by adjusting the domain. But as it stands, it's not a function. Okay, Let's answer just one question of a little different type. How many different functions from 1, 3, 5 to 2, 4 are possible? So here's 1, 3, 5. And over here is 2, 4. And I want to define a function. So I could do this, for example, goes here, this goes here, and this goes here. That's a legal definition of a function, so that's one possibility. Another possibility would be to take all three items and send them to 2. So that's a different possibility, so there has to be at least 2 choices. In fact, there are going to be more. If you can see ahead of time what's happening, let's just talk about choices, consecutive choices. I start with 1. I have 2 choices. I can either take that, the function can either take that to 2 or to 4. So 2 choices for f of 1. Same for 3. 2 choices for f of 3. And same for 5. 2 choices for f of 5. And these choices are independent. What I do with 3 has nothing to do with what I do with 1. So the right thing by the multiplication rule is to multiply these, and there are 2 cubed equals 8 different functions. Okay, this type of procedure then, or thought process, works for any type of function where the domain and the codomain are finite sets. I can always then just list how many choices there are for each input and how many inputs there are. Some of the examples we were looking at had infinite domains, like here was an example of a function. And the domain and codomain here were infinite, so there would be an infinite number of such functions that might do the same thing in a different situation. Okay, let's look at one more topic here. I'm sure you've heard the term range before. In fact, you probably heard the term range long before you heard the term codomain. So let's approach this with a couple of pictures again. Here's a function from A to B by the rule f. And reading this carefully, the range of f, where f is a function from A to B, is denoted by this. Okay, have to get used to some notation here. This doesn't mean that I take set A and plug it into the function. This is just notation. It means conceptually that I take all of the possible inputs, plug them into the function, and say what are all the possible outputs. So here's a careful statement of that. The range of f are all the elements of the codomain. So first of all, the range of f is going to live over here somewhere. And it's all the members of the codomain which are the output of the function for some possible input. So over here, here's an input, here's an input, here's an input in the domain. And maybe this maps over here, and this maps over here, and this maps over here. But there might be other guys over here. This one, and this one, and this one. So what's the key check? The range consists of the elements which are actually possible outputs. It's right here. this set of three guys in my picture is f of a. There were elements in the domain that went to these guys, so they're part of the range. There were no elements in the domain that went to these guys, so these guys are in the codomain, but they're not in the range. Then you can see that the range is a subset of the codomain. Maybe all of it, or maybe just part of it, like in my picture. Another thing that we're going to talk about is the inverse image. Let me draw another function diagram. Here's the domain A, the codomain B, and the inverse image, we talk about the inverse image of a set in the codomain. So over here, I'm going to draw a subset, call it C, and then let me populate this. So here are a couple of guys, and here's a couple of elements outside. And suppose back over here that this goes here, and this goes here, and this goes here, and this goes here. So when we talk about the inverse image of this set, it's somebody that lives back here in the domain. It's all of the members of the domain, in fact, which produce an output in C. And so in my picture, that's right here. This is F inverse of C. Again, this is notation. Next class period, I guess, we'll start talking about inverse functions. This doesn't mean that. This just means kind of the reverse relationship. What, if I start over here with a set C, what kinds of things can I put into F that will go to those elements of C in C? Let's look at an example. Same picture as before. And I ask, what is the range of F? Notation for that could be F of A. And it's the range, remember, lives in the codomain. It's the set of all possible outputs of this function. So in this case, 2, 4, and 10 are outputs of the function. The other members of the codomain are not outputs, and so this is it. And what about the inverse image of 2, 4? So the set C is the set 2, 4. So it's the set of everybody in the domain which either maps to 2 or to 4. What is that? Well, 1 maps to 2, and 5 also maps to 2, and 2 maps to 4, and that's it. F of each of these guys is in the set 2, 4, so this is the inverse image. How about F inverse of 6, 8, 12? It's all of the members of A that map either to 6 or 8 or 12, and you rightfully say there aren't any. Okay, so the inverse image is the empty set. Okay, so let's finish with one more example, a little more involved. Let's take a function from the non-negative real numbers, so this is 0 and all positive real numbers, to the integers, and let's work it this way. F of x equals, first we'll take x, square it, add 1, and then take the floor as we talked about before. So because x squared plus 1 is a function, and we know the floor function is indeed a function, we showed that before, when I put these two things together, it's still a well-defined function. This is a function. Let's see about the inverse image of 1, 2. So what does this mean again? This is all of the non-negative real numbers, which when I put them in this function, I either get 1 or I get 2. Okay, so I can do this separately actually. There are only two possibilities. So let's find everything that goes to 1, then find everything that goes to 2, and we'll just combine them. Like up here, I found everything that went to 2, that was 1 and 5, and everything that went to 4, that was 2, and then just put them together in a union. So, what goes to 1? That is, to solve the equation a squared plus 1 floor equals 1. Solve this for a. Why am I doing this? I'm trying to compute, so a is being input into the function. Here's the output. When is the output equal to 1? So for which a's, when I put them into the function, do I get 1? Okay, let's unpack this. When is the floor of a squared plus 1 going to be equal to 1? Well, it's when a squared plus 1 itself is greater than or equal to 1 and less than the next higher integer, 2. And when is that true? So now it's more familiar. Algebraically, let's solve this. Subtract 1 from all three sides, so to speak, of this compound inequality. 0 less than or equal to a squared less than 1. And now I'm going to take the square root. Notice there are no problems. 0 and 1 are non-negative, and a is 2 because it comes from r non-negative. So when I take the square root like this, square root of 0 is going to be less than or equal to a less than square root of 1, but this is just 0 less than or equal to a less than 1. Numbers in this range, when I put them in here, square them, add 1, and take the floor, I get 1. Then let's do that for 2. So what goes to 2? So then I'm supposed to solve floor of a squared plus 1 equals 2. And this is going to be real similar then. So we'll speed it up just a little bit. 2 less than or equal to a squared plus 1 less than 3. Subtract 1, 1 less than or equal to a squared less than 2. And take square root. The square root of 1 is 1 less than or equal to a less than square root 2. And now put them together. That is a union. So let's come back up here. This is going to be, alright, it's everything greater than or equal to 0 up to but not including 1, but then I pick up 1 here and then go on up to square root of 2 but not including. So let's use interval notation like you would in a calculus class. It's closed interval on the left, 0, up to square root of 2, open interval on the right. So square root of 2 not included. All of these guys, and exactly these guys, when I plug them in here, square them, add 1, take the floor, I get either 1 or 2. Second part of the question, find the range, is what this question is saying, f of all non-negative numbers. So first of all, note that when I square something, add 1, and take the floor, I am going to get a positive number. Why is that? Well, when I take something and square it, a non-negative number or any real number actually, and square it, I get something greater than or equal to 0. I add 1, I get something greater than or equal to 1. I take the floor, so I drop down to the next integer, which is no smaller than that. But if I'm already at 1, I don't have to drop any below 1. And so this gives a positive number, more specifically a positive integer. So what I'm saying at the moment is f of r non-negative, the range is contained in z plus, positive integers. I'm trying to find out what set this is. I know that it's inside z plus. If I could show that z plus is inside this set as well, then these two things would be equal, if you remember how we showed that two sets are equal. So let's think about that a little bit. Given somebody in z plus is it in f of r non-negative? Well, another way to say this is so this is saying, is it in the range? It is in the range if there is an integer, say a, in r non-negative, for which f of a equals b. This is what it means to be in the range. B, the number b is in the range if there's a number in the domain which goes to b. And so if a squared plus 1 equals b for some a in r non-negative. So b is in the range if this equation has a solution. If I can find an a which makes this work. Okay, so b is fixed for a moment, and I say, man, can I find something that really makes this equation true? And the floor is what makes it look tricky, but if you think about it, if a squared plus 1 itself is equal to b, then the equation is true, right? If a squared plus 1 is already an integer, and b is an integer, then a squared plus 1 floor equals a squared plus 1 equals b, and it works. So I really can solve the equation without the floor if I want, and this then is easier. A should be square root of b minus 1. Can I always take the square root? Yes, because b is a positive integer, so b is always greater than or equal to 1. You say a is not an integer. Well, it doesn't have to be. A can be a non-negative real number. But you give me any integer like 18, and I can compute a real non-negative real number a, which satisfies this equation. So what we have just shown here is that z plus, not z star, but z plus, is contained in the range. And so if I have containment this way and containment this way, I have inequality. Let's write it up here. The range of this function is the set of positive integers. And we'll stop there. Thanks.